Okay, so you should all be familiar with the distance formula in 2 dimensions. What we want to do is extend that out to 3 dimensions. Hopefully my drawing capabilities won't make that impossible. So first of all, here we have, let's review the distance formula in 2 dimensions. So here's a xy plane. Okay, and let's just throw 2 random points onto the xy plane. Let's say we have this point P right here and another point Q right there, and we want to find the length of that line segment, PQ, right? So, and there's a longer version of the formula, but basically what it comes down to is we have a right triangle here, okay? And there is a delta X value and a delta Y value. And if we want to find, let's say, I'll use L for the distance between the points, all right? We can take, say that L is the square root of delta X squared plus delta Y squared, right? So in this particular case, it looks like P is at -1, -1, and Q is at, let's see, that looks like 1, 2, 3, 2. Okay, so what is our delta X value? Our delta X, we went from -1 to 1, so that's 3 minus -1, or 4. Okay, our delta Y value, we go from, if we start at P and go to Q, we go from -1 to 2. So that's 2 minus -1, which is 3. Okay, so we end up with L. Oh, I think this might be a very nice answer. We end up with the 4 squared plus 3 squared. If you do the math real quickly, that's the square root of 25. So L is exactly 5. Usually the answer doesn't come out to be so nice, but in this case, it's a rational answer because I didn't mean to, but I drew a 3, 4, 5 right triangle. So that's how we find the length. It's basically, we just use the Pythagorean theorem, right? Now, what happens if we have 2 points in 3-dimensional space? Well, first, I'm just going to sort of assume that one of those points is the origin, all right? It wouldn't have to be the origin, but let me put my X, Y, Z plane out here. We had before, okay? So our first point we'll just put right at the origin, okay? The second point, I am going to actually start to draw sides to go with it. So the second point, I'm going to go that far in the X direction, and I'm going to go this far in the Y direction. Now I could have first, now this is critical here, I could have gone in the Y direction first and then the X direction. And you can see, while it looks kind of like a parallelogram in our picture, that would actually be a rectangle in the X and Y plane. Then we would come up a certain distance Z. So we're already here and we're going to come up a certain distance Z to get to our final point. Let me put the point boldly in green, okay? So there's our point, okay? So we could go over a certain, let's call this delta X. If it had been between a point, it's X because it's not we're going from the origin. We started at the origin, but if we had started somewhere besides the origin, we would go a delta X, a delta Y, and then we would go a delta Z to get up here, okay? But we could have, as we just said, we could have gone delta Y, delta X, then delta Z, or we could go delta X, well, we could go delta Z first. So that would bring me up like this. And then we could go out our delta X to bring me over here. And then I could go my delta Y, okay? But I could do these things in any order. And you could see that, okay, if I do them in different orders, I get all the possibilities to kind of form a box. Okay. So what we're really finding is this distance from one corner of a box to the opposite corner of the box. Okay, so from our perspective, we're kind of connecting the back left corner to the front right corner. Okay. Well, to do that, we want to figure out what that length is. Okay, so to do this, we're going to add a couple of lines here. The first line cuts right across the XZ plane. Okay, so that's the diagonal of a rectangle. Well, the diagonal of a rectangle, we know how to do. We can get use the distance formula that we had before, and then we're going to add to it another side. Okay. Now, hopefully, what you can see in here is that we have a couple of right triangles. Okay. In the XZ plane, this was in red. That's a rectangle. So we have a right. If we cut it in half with the white line, let me call that L1. Okay. That first diagonal is going to be the hypotenuse of a right triangle in the XY plane. Okay. Then we have another right triangle here. I should probably draw the corner sort of like that. Whoops, this will be L2. Okay. Where the legs of that right triangle are L1 and L2. Okay. So the first right triangle would have this relationship. L1 squared is equal to the leg delta x squared plus the leg delta y squared. All right. The second triangle, we'll use L for the overall diagonal length, would have L squared equal to L1 squared plus L2 squared. Okay. Well, we can substitute in, okay, some things. We can substitute in for L1 squared, we can substitute in delta x squared plus delta y squared. And what can we substitute in for L2? That is just delta z. And we'll square it since it's L2 squared. And because addition is commutative, we can say L squared is just delta x squared plus delta y squared plus delta z squared. This is a 3D Pythagorean theorem. Okay, in the 2D version of this would have simply been that L squared is delta x squared plus delta y squared. We often then take the square root of the entire right-hand side, but this is the 2D version. The 3D version, we just add on delta z squared. Now, the really abstract thing, which I can't draw at all, is we can go beyond 3D. We can use the Pythagorean theorem in as many dimensions as we like, and we can talk about distances beyond 3 dimensions. You can do 4 or 5 or even an unlimited number of dimensions. And that comes up in statistics a fair amount. If you think of each data point as sort of adding a dimension to your data, then you could easily have 1,000 data points. So you kind of have a 1,000-dimensional kind of problem that you're working out. But for now, let's not expand our minds too much. Let's just go from 2D to 3D. Now let's just do a quick example. Let's say I had the point that's not at the origin. Point P is at 2, 0, 3. Point Q is at -1, 2, we'll go with 1. And I want to find the distance between P and Q. Okay, so I would need to know what a delta x value is, a delta y value, and a delta z value. Okay, so x, if we start at P and go to Q, we always take Q minus P. So -1 minus 2, we go down 3 in the x direction. Okay, the value decreases by 3. In the y direction, we went from 0 to 2, so that's 2 minus 0. We went 2 units in the y direction to get from 0 to 2. And to get from 3 to 1, that's 1 minus 3. Okay, so that is -2 units in the z direction. Now remember, squaring removes the negative sign, so I recommend when you go to find L, in green here. Okay, so when I go to find, I'll say L squared is equal to, I'll just do 3 squared because 3 squared and -3 squared are the same. And you're not likely to, in entering the negative in the calculator, we can make the error of taking the negative of 3 squared, which is -9. Okay, so just use 3 squared plus 2 squared plus 2 squared again. So L squared is equal to 9 plus 4 plus 4. I believe that's 17. Okay, so the length of this line connecting P to Q would be the square root of 17.